guys, today we are going to do 3-6 solving systems of using matrices. So you will be able to represent a system of linear equations with a matrix, and you will be able to solve a system of linear equations using matrices. Our big idea: you can use a matrix to represent and solve a system of equations without writing variables. The first thing we need to get to know is, what is a matrix? So, a matrix is a rectangular array of numbers. You usually display the array within brackets, as you can see in our example, and the dimensions of a matrix are the numbers of rows and the numbers of columns in the array. So, when we're saying the dimensions of a matrix, we do rows by columns. Here in our example, we have matrix A. We have 2 rows and 3 columns. So this is a 2 by 3 matrix. That's how we say 2x3, 2 by 3. And you can write it as A 2 by 3. Then each number in a matrix is called a matrix element. You can identify a matrix element by its row and column numbers. So in matrix A, we have element A1, 2. And this is the element in row 1, column 2. So the first type of problem is identifying a matrix element. We want to find the element A23 in matrix A. So we're going to the second row, third column. We're going to the second row, third column. So in that third column and second row, we have the element 8, which is A23. You can represent a system of equations efficiently with a matrix. Each matrix row represents an equation. The last matrix column shows the constants to the right of the equal signs. Each of the other columns show the coefficients of one of the variables. So we have a system of equations here. X plus 3y equals 7, and 3x plus y equals negative 8. In our first column, we have 1 and 3, which is representing the x coefficients. We then have, in our second column, 3, 1, which represents our y coefficients. Then, all the way to the right, in our last column, we have 7, negative 8, which are our constants. We would draw a vertical line to replace the equal sign so that we can separate the coefficients from our constants. How can you represent the system of equations with a matrix? So, just like we had before, we want to write it in brackets. We have our x coefficients, which is 2 and 1. Then we have our y coefficients, which is 1 and negative 6. We are going to use, instead of the equal sign, we're going to draw a vertical line. And on the other side of our vertical line, we're going to write our constants, 9 and negative 1. Go ahead and represent those two bottom systems of equations in a matrix. Problem 3, we are going to write a system from a matrix. So we have our matrix, but now we want to go in the opposite direction and write this system of equations. So we have to remember that each row represents the coefficients of our variables. And on the other side of that vertical line is our constants. So we have the coefficients for x first, which is 5x and 0x. Then we have our coefficients for y, plus 2y plus y is equal to 7 and is equal to 9. Since we have 0x, we don't need to write that, so our system of equations would be 5x plus 2y equals 7 and y is equal to 9. You can use a matrix that represents a system of equations to solve the system. In this way, you do not have to write the variables. So, to solve the system using the matrix, use the steps for solving by elimination. Each step is a row operation. Our goal in this is to use row operations to get a matrix in the form 1, 0, 0, 1 and equal to A and B, where A and B are constants, or 1, 0, 0, A, 0, 1, 0, B, 0, 0, 1, C, where A, B, and C are constants. So, notice, the first matrix represents the system x equals A and y equals B, which will then be the solution of a system of two equations in two unknowns. The second matrix represents the system x equals A, y equals B, z equals C. So, different row operations that we can use. We can switch any two rows. So we can have 2, -1, 3, 3, 2, 5, and we could switch them, and they would become 3, 2, 5, 2, -3, 3, -1, 3. We can multiply a row by a constant. So if we take that bottom row and multiply it by 2, we would multiply each element by 2. Then we could add one row to another row. So we took the bottom row and added it to the top row. We are taking that bottom row and adding it to the top row, so we do 3 plus 4, 2 plus -2, and 5 plus 6 to get in the top row 7, 0, and 11. We can also combine any of these operations as well. So we are going to solve this system using a matrix. First, we're going to write the matrix for the system. We have 1, 4, -1, 2, 5, 4. We have to remember what our goal is. Our goal is to get that diagonal of 1 and the rest of the elements to be 0. So, my first element is 1. So now I'm going to go down and look at 2. I want to make 2 a 0. So I'm going to multiply row 1 by -2. And I'm going to add it to row 2. So now I have -2 times 1 plus 2 is 0. -2 times 4 is -8, plus 5 is -3. Then I'm going to have 8 plus 4. Sorry, that's supposed to be a -1. So 2 plus 4, which is 6. Now this is going to replace that second row. So now I have 1, 4, -1, 0, -3, 6. And I'm going to multiply row 2 by 1/3, so I can have that -3 be a -1. Be a 1. So I'm going to multiply by -1/3 on the second row. And I'm going to have a new matrix of 1, 4, -1, 0, 1, 2. -2, I'm sorry. Now I need to multiply row 2 by -4 and add to row 1 so that I could get rid of that 4 in row 1. So I'm going to add row 1 to -4 times row 2. 1 plus 0 is 1. 4 plus -4 is 0. -1 plus 8 is 7. I'm going to replace row 1 with my sum. So I have 1, 0, 7, 0, 1, -2. Since we now have the diagonal of 1 and zeros in all of my other elements, I have the solution to my system. X is equal to 7 and y is equal to -2, which is the solution of 7, -2. Matrices that represent the solution of a system, which we just got where our diagonals were all 1, are in reduced row echelon form. Many calculators, which we will be doing tomorrow in class, will be doing this function to be able to check our work with matrices. So this function will do all the row operations for you, and you will be able to solve the system.